Good day! I am Sophia Nang, ID 121, and today I will be teaching you guys CALENG3 quiz number 2. So the topics I will be discussing in this video are the applications of differential equations, which can be categorized into 6 equations. These are the exponential growth, the exponential decay, the logistics equation, the Newton's law of cooling, mixing solutions, and electrical circuits. Okay, like I said a while ago, we will now be discussing the 6 different differential application equations. The first one being exponential growth. I have here written the way you integrate the exponential growth equation. So first you start off with this one over here, and then you end up with this one right here. So this is how it looks like. Now you might be wondering, hey, what if you don't have an infinite population? Well, I'll tell you more about that later once we get to logistics equation. First, let's discuss the exponential decay, which is basically just the opposite direction of exponential growth. As you can see here, the k in exponential growth should be greater than 0, while the k in exponential decay should be less than 0. Now, next we have our logistics equation. Like I mentioned a while ago, this one takes into consideration the population. So first, the first difference between this one and exponential growth is that you will have to do a partial function once you integrate this side of the equation. As you can see here, I already wrote the integration, so just take a look at it. And yeah, this should be the equation you end up with after integration. So A here represents your total population, X is your infected quote-unquote population, and then K is your constant, T is your time, C is another constant. Okay, so this is how the graph looks like. Your total population will be one of the asymptotes of the graph, and as you can see, it starts from 0, ramps up, and hits your total population eventually. So next we have Newton's law of cooling, which has the following equation. Your du over dt is the change in temperature over time. Your U is the object temperature, and your UA is the ambient temperature as represented by the A. Now, written here again is the integration, and eventually you will get this equation. Now, Newton's law of cooling does have restrictions because of its simplistic nature, so these are the following. Number 1 is no chemical reactions, because chemical reactions can release or take heat, which would significantly disrupt Newton's law of cooling. Number 2 is that there are no phase changes, because when a substance changes phase, it tends to plateau the temperature, which would interrupt, again, Newton's law of cooling and its projected path. Number 3 is no radiative heat, which basically means that your object cannot influence the room's temperature, which makes sense given that your ambient temperature is supposed to be a constant in your solution. And finally, the last one is that your object is uniformly heated, or the whole thing has a uniform temperature. Okay, next we have mixing solutions, which have 3 given equations. The first one is your total volume, which is your initial volume plus how much stuff is coming in, which is the difference between your inward flow and your outward flow over time. After that, we have the equation for the concentration of salt in your mixture. Now you have to assume that this one is non-reactive, because if it was reactive, the concentration would be constant, right? So it is your flow in times your concentration in equals your flow out times your concentration out plus any other salt that comes through. So here I have drew like a simple reactor that shows my point. Now, usually your vat can have a specific volume, but if there's no specified volume given, you can assume that it is infinite. Now, lastly, we have the C app, which is X, which is the amount of salt over V, which is, this represents basically that it's perfectly mixed and in even concentration. Now, I will discuss further how to solve for this one. This does turn out to be a linear equation. So, but then it is dependent on your problem. So your px and qx, so on and so forth. I will discuss it more given the examples. And lastly, we have the electrical circuits, which is your current times resistance plus inductance times current over time plus charge over capacitance is equal to your EMF. I wrote what all of them represent right here, so just take a look. Now, your current can be represented as charge over time, and usually that's what you need to take note of during problem solving. And furthermore, RLC circuits, which means that this one, and this one are all present, will not show up because this is considered as a second order derivative, which is not included within the scope of quiz 2. Now, onto the examples. Okay, so for our first example, a tank is half filled with pure water. The inlet water flows at 1,200 gallons per minute with an unknown concentration of brine, and the outlet flow of water flows at a rate of 900 gallons per minute. After 30 minutes, the tank is 80% full. When it is full, there is 500 pounds of salt. What is the concentration of the entering brine? Now, right here, I've written all of our givens. And so first step is to get the capacity of your tank. So since it says here at 30 minutes, your tank is 80% full, that means at 0.8 of your capacity, your total volume will be equal to your initial volume plus the flow, like the amount of water that came in after 30 minutes. So this simplifies into this. Once you've gotten your total, which is this one, so since it's half, this is half of 30,000, and then the difference between 1,200 and 900 is 300, and then this one is for time. So yeah. Okay, so now this one is one of the formulas we were talking about a while ago, which was Q in C in is equal to Q out C out plus dx over dt. Now, this one is just when you plug in all the values. This one is given. These two were given. This one is what you're looking for. This one is your amount of salt. And this one is your volume at any given time. And this one is your change in salt over time, like I mentioned a while ago. So now, after you simplify this is what you get. And then once it's in this form, you'll be able to perform linear equation solving. So our px is the one with an x in it, which is this one. So that's 3 over 50 plus t. And then our qx is this one. All right, so first we have to find the integrating factor, which is after doing this thing that you've learned in quiz 1, you'll get this one as your integrating factor. So now it's just Vx equal to the integration of Vqx dt plus c. Replace all the values with what you were given here. And then after some simplification, this is your final equation for the amount of salt at any given time. So we're given 2 points to consider in this problem, which is at time 0, your salt is equal to 0, since it did mention that it was pure water. So at this time, you can plug in what you got here to here. And then after that, you'll be able to replace your constant with C in. After that, our second point is that at 50 minutes, our amount of salt is 500. You can get this from extrapolating the time a while ago, since it did mention that at 30 minutes, your water is 80% full. So after figuring out this point, you'll be able to get the concentration in after some simplification, which means that your final answer is 0.178 liters per gallon. So next, we have an electrical circuit problem, which reads the following. An electric circuit contains an EMF of 100 volts, this one, a resistor of 20 ohms, this one, and an inductor of 1 Henry. So, assuming that there's no current at t equals 0 seconds, find the current at t equals 10 seconds. All right, so this is our given, and this is the equation that I was discussing a while ago. Since there is no current or capacitance given, this one can be struck out, and we'll be left with this one, which is a linear equation. So filling in the details we were given a while ago here, we'll be able to sort this out into a linear equation and find out what our px and qx are. Okay, after that, we'll be getting the integration factor, which is equal to e raised to 20t. And then we'll plug it in like a while ago, says vx is equal to the integral of v qx dt plus c, like that. So after integration and simplification, we'll be able to get the equation for our current. All right, so at t equals 0, our current is equal to 0. So with this, we'll be able to get our constant at time equals 10. Plugging that in from here, we'll be able to find out that your current is still 5 amperes. This is because this value in general is very close to 0, so there's virtually no change. So for this third question, we have an exponential decay equation, right? So what we're given is that So what we're given is that a fossilized bone is found to have 0.3% of its original amount of C14. How old is the fossil if the half-life of C14 is 5,730 years? Okay, so at time equals 0, our amount of C14 is equal to a certain number, which is x, right? At time equals 5,730 years, our x is equal to half whatever our given quantity was at time equals 0. At a questionable time, that is the time that we're trying to look for, our x is equal to 0.003%, 0.003 of the amount initially, right? As you can see here. So bum, bum, bum. Okay, so this is the K equation. So what we'll do is we'll use each of these points to find out the constants in our equation so that we'll be able to find out the time. Okay, so first at t equals 0 and x is equal to x, that means our constant is equal to x. At the half-life, like this, we'll be able to cancel both sides, like that. So 0.5 is equal to e raised to k times 5,730. So applying logarithm on both sides of the equation will make it so that your k is equal to ln 0.5 over 5,730. Now that we have both of our constants, we'll be able to find for the time, given that only 0.003 of the C14 remains. Boom, boom. Okay, so first cancel both of these and then apply ln to both sides. Afterwards, multiply by 5,730 and divide by ln 0.5. After that, you'll be able to get the time, which is equal to 48,022 years. See? Easy. Okay, so for this number, we have Newton's law of cooling, and the problem reads as such. It is scorching outside. You take a thermometer that is 2 degrees Celsius outside, and after 3 minutes, the temperature is now 36 degrees Celsius below the surrounding temperature. After another 4 minutes, the temperature is only 21 degrees Celsius below the surrounding temperature. What is the surrounding temperature if it is constant? Okay, so let's enumerate our given. So at time equals 0, that means you haven't taken out the thermometer yet. Our temperature is at 2 degrees Celsius. At 3 minutes, our temperature goes up to the ambient temperature minus 36 as it is written in the problem. And then 4 minutes later, which is 3 plus 4 equal to 7 here, our temperature is now the ambient temperature minus 21. Okay, so I'd like to remind everyone that this is still an integration problem. So you can put the limits like this so that you can solve for AK. Afterwards, you go back to this one, which is our usual integration, and through this, you'll be able to find another K. Just take a look at this. This is nothing beyond what we've done before. So afterwards, we'll be able to equate the two Ks together into this equation. And then after some simplifications, that we'll be able to get this isolated. For example, we did the reciprocal of both sides here, so that we'll be able to isolate UA here. We should get the answer of 55.93 degrees Celsius. Thank you so much for watching. You may also avail syntax tutorials by scanning the QR code flashed on your screens. Once again, this is Sophia Nang from Syntax, paving your way to excellence.